Today, we are diving into one of the most incredible stories in the history of science. It's this whirlwind, half-century sprint where humanity went from thinking atoms were just tiny, solid balls to, well, unlocking the immense power hidden right at their core. Seriously, it's a story packed with genius, surprises, and a complete revolution in how we see the universe.
A classic textbook on this, Irving Kaplan's Nuclear Physics, puts it perfectly. This whole journey wasn't just about cold hard facts and equations. It was really driven by imagination, by intuition, and believe it or not, a real sense of beauty in the patterns of the universe. Think about it. For most of history, the atom was just an idea, a philosophical concept. Then, by the 1800s, it felt like we had it figured out. It was a scientific reality, the fundamental, indivisible building block of everything. But as physicists started to poke and prod at it, they realized the story was way, way more complicated. So what is an atom really?
Okay, so let's set the scene. We're in the late 19th century, and it's a time of huge confidence in science. The feeling was that we were just filling in the last few details of a mostly complete picture. Matter was made of atoms, and atoms, well, they behaved in nice, predictable ways. And the foundation for all this confidence was John Dalton's atomic theory. It was just beautifully simple. Every element, gold, oxygen, whatever, is made of its own unique type of atom. You can think of them like a set of microscopic billiard balls. And, crucially, these atoms are uncuttable. They're the smallest thing there is. This model was a huge success. It just perfectly explained all the laws of chemistry at the time. And this whole mindset got a massive boost when Mendeleev created the periodic table. By arranging the elements by their atomic weight, he found this stunning, repeating pattern in their chemical properties. It was like somebody had finally cracked the secret code for all of matter. Everything was orderly, it was predictable, and it all made sense. But just as physicists were getting comfortable with this neat and tidy picture, strange new discoveries started to pop up in labs all across Europe. And these were things that the simple clockwork model of the atom just couldn't explain. The foundation was about to crack. First up, X-rays, this invisible energy that could pass right through your hand. I mean, how could rays pass through solid atoms? Then came radioactivity. Marie and Pierre Curie discovered that elements like uranium were constantly spewing out energy, all on their own. And this is the crucial part. Marie Curie proved this wasn't some kind of chemical reaction. The energy was coming from inside the atom itself. And then came the final blow to that old model. J.J. Thomson discovered the electron, a particle nearly 2,000 times lighter than the lightest atom, hydrogen. So the indivisible atom wasn't indivisible at all. It had parts. A tiny, negatively charged piece could actually be chipped right off of it. So the race was on. If atoms have these tiny negative electrons inside them, but are electrically neutral overall, well, there must be some positive charge in there to balance things out. The big question was, how were all these positive and negative parts arranged? So J.J. Thomson, the guy who found the electron, he made the first educated guess. He pictured the atom as something he called a plum pudding. A better way to think of it today would be like a chocolate chip cookie, a diffuse, spongy ball of positive dough with these small negative electrons dotted throughout it like chocolate chips. It was a simple, logical first step. But one of Thomson's former students, a guy named Ernest Rutherford, decided to actually test this model. He came up with this brilliant experiment. He would fire tiny, positively charged bullets, called alpha particles, at an incredibly thin sheet of gold foil. Now, if the plum pudding model was right, these particles should just punch right through the soft pudding with no problem. The result was absolutely astonishing. While most of the particles sailed straight through, just as expected, about 1 in every 8,000 of them bounced back violently. Rutherford later said it was as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. The conclusion was undeniable. The atom wasn't a soft pudding, it was almost entirely empty space, with a minuscule, incredibly dense, positively charged nucleus right at its very center. This new model was then fine-tuned by Henry Moseley. He proved that an element's true identity, what makes lead lead and gold gold, comes from the number of positive charges, or protons, in its nucleus. This, not its total weight, was the fundamental rule of matter. The atomic number defined the element, and it was all locked away in that tiny nucleus. The nucleus was everything. So, with the atom structure finally understood,
The next question was just inevitable, and honestly a little terrifying. What happens if you try to break the nucleus itself?
For a decade, the nucleus really resisted. I mean, firing positive protons at it was tough because they'd just be repelled by the positive charge of the nucleus. But in 1932, James Chadwick discovered the neutron, a particle with mass but no charge, living right there inside the nucleus. It was the perfect subatomic bullet. It could slip right past the atom's electrical defenses and strike the core.
So, when physicists started firing these new neutron bullets at uranium, the heaviest element they knew, the result changed the world. The nucleus split into two smaller pieces, a process they called fission, and it released a tremendous burst of energy. But even more importantly, that split also released a few extra neutrons. And each of those new neutrons could then fly off, split another uranium atom, releasing more energy and more neutrons in an explosive chain reaction. Now, this new atomic and nuclear world was completely invisible. To explore it, scientists couldn't use their old tools. They had to invent entirely new ways of seeing and interacting with this subatomic realm, machines that were every bit as revolutionary as the discoveries they made possible. I mean, it's a pretty fundamental problem, right? If you can't see the particles themselves, how on earth can you track their movements and interactions to figure out what they're doing?
Well, the answer was the Wilson cloud chamber, and it's a truly ingenious device. It basically creates a small, artificial cloud inside a box. When a charged particle zips through this vapor, it forces tiny droplets to condense right along its path, leaving a visible trail. It looks just like a jet's contrail in the sky. For the very first time, scientists could literally take pictures of particle tracks and see the results of subatomic collisions. Okay, so natural radioactivity gave them their first bullets, but they're kind of slow and not very precise. To really probe the nucleus, to really get in there, scientists needed a way to create and aim their own powerful, high-energy projectiles. And this need gave rise to particle accelerators, machines like the cyclotron. They basically act like giant subatomic slingshots. They use powerful magnets to swing particles around and around in a spiral, and an electric field gives them a little kick of energy with each pass. This gets them going at incredible speeds before aiming them at a target. This was really the birth of big science, the massive tools that would smash open the remaining secrets of the nucleus. So just think about that. In the span of a single human lifetime, from about 1895 to 1945, our entire picture of reality was completely redrawn. We went from seeing the atom as an unbreakable solid ball to a miniature solar system whose central sun contained almost unimaginable power. It really makes you wonder, doesn't it? What revolutionary discovery is sitting just beyond our horizon today?